The first part of this screencast is especially for those of you who don't remember your chemistry or haven't had it for a while, and it has to do with reviewing the ideal gas law. This would be a gas that's under ordinary pressures and temperatures, not extremely high pressures and extremely low temperatures. When we look at a gas then, let's say it's in a balloon, we would know that the volume is going to be directly proportional to the temperature, because as the temperature gets greater, the particles of gas move around faster and faster and have more energy, and the volume of the gas expands. We also know that if you put pressure on the gas, the volume is inversely proportional to the pressure. The more pressure, the smaller the volume. And you can think of basketballs and automobile tires and balloons in order to imagine that this is true. And then another common sense idea, of course, is that the volume is going to be directly proportional to the quantity of gas that is in the container. We use the letter N to represent the number of moles. Remember, a mole is a very, very large number of particles. It has a number of Avogadro's number, which is 6.022 times 10 to the 23rd, and a little bit more about that a little bit later. So when I put all three of these ideas together, that volume is going to be proportional to the amount of gas in moles, the temperature of the gas inversely proportional to the pressure. I obviously need a proportionality constant, so we can say that volume equals some proportionality constant. We'll call that R times NT over P, and the R stands for a person's name. And then if I rearrange my terms, I get the very familiar PV equals nRT. And if we come over to the next page, we're going to be heading in the direction of that formula. Why did we choose 6.022 times 10 to the 23rd? Well, that's a definition. It comes from the definition that if we let carbon, which is a very, very stable element, and its most common and stable isotope, carbon-12, we call that carbon-12s. So if you divide by 12, you get 1, which is the atomic mass of hydrogen. So hydrogen begins with a mass of 1, and we get bigger from there. This right there, the U, is sometimes called an atomic mass unit, and sometimes it's named after John Dalton. It's called a Dalton. So by definition in chemistry, 1/12 of the mass of a carbon-12 atom is 1 atomic mass unit. And those are the numbers in red on at least the periodic table in my room. It's the mass number. Now, when you begin to say how many atoms of carbon does it take to have a mass of 12, and of course this is rounded off. We're only going to the ones place here. We actually know these atomic masses to many more significant digits than this. But 12 grams of carbon would have Avogadro's number of particles. And you pick any element on the periodic table, and its mass number, we could talk about the atomic mass of oxygen, 16. 16 grams would have Avogadro's number of particles. 1 gram of hydrogen would have Avogadro's number of particles. 238 for uranium would have Avogadro's number of particles. And that's pretty much a review. Now, there's our PV equals inert, the ideal gas law. And if you solve this equation for R equals PV over NT, And you can then ask this question: if I have a certain pressure and a certain volume and a certain amount of gas and a certain temperature, and I change it to a different pressure and a different volume and a different amount of gas and a different temperature, if I know any 7 of those 8 values, I can find the 8th value. That's often called the general gas law. So we have the ideal gas law here and the general gas law there. Now, most of the time, the amount of gas under consideration is constant, so N would cancel out because it would be the same. You can also see, if you remember your chemistry, that Boyle's law, which is the relationship between pressure and volume, would imply that the temperature is constant. And if the temperature is constant, then you would have PV1 equals PV2, Boyle's law. Or Charles' law would have the pressure constant, and so the pressure would cancel out, and Charles' law would be V1 over T1 equals V2 over T2. R is the universal gas constant, and it depends especially on what you're going to use for pressure. If you're going to be using pascals for pressure, this is the constant you need to use. If you're going to be using atmospheres for pressure, you must use this constant right here. And there are lots of other constants as well, because there are many different units of pressure, like the bar and the millibar, and millimeters of mercury, also known as a torr. But the point being that make sure, and this is the common mistake in science problems having to do with gases, make sure your universal gas constant R agrees with the pressure that you're going to be putting in for P. Now, let's take a look at some math problems. An ideal gas at 20 degrees Celsius and a pressure of this many pascals in a container having a volume of 1 liter. Notice the reason I circled this is because right off the bat you should say that's degrees Celsius, but we're going to need absolute temperature. We're going to need to have this value of temperature in Kelvin. And that's what you're reminded about right here. So you're going to have to add 273. In fact, it might even be better to use 273.15 if you need those extra significant digits. Since this digit goes to the tens place, I would probably go ahead and use this and then round off this answer to the tens place because I'm adding, if I want to be a little bit more in keeping with the rules of significant digits. Now, in this problem, we're being asked to find how many moles. So the number of moles is PV over RT, and now I put in my pressure, I put in my volume, which happens to be in cubic meters and not liters, and then my temperature there's my Kelvin temperature, and if I'm in pascals, I need to be in, I need the constant that's in joules. And in case you don't know why, you come over here. A pascal is a Newton per meter squared. And if I multiply the numerator and the denominator by meters, I get Newton meters per meters cubed. And a Newton meter is a joule. So now I have joules per meter cubed. And since I now have joules per meter cubed for my pascals, you can begin to see how my joules will cancel out. Joules will cancel there and there. And my meters cubed are going to cancel out, denominator and numerator. And here I have moles in the denominator of the denominator. I mean Kelvin in the denominator of the denominator, and Kelvin in the denominator. So that's going to cancel. And what I have left is moles that's in the denominator of the denominator, which puts it in the numerator. my answer comes out to be moles. We can also find the temperature in Kelvin if we, and let's go back and double check the problem in part B, find the temperature after the gas expands to 2 liters. So now I have a new volume, and I'm going to come up here, and again I just could have used PV over NT equals PV over NT, 111, 222. The amount of gas doesn't change like normal, and I'm going to solve this for my final temperature, and this is just a pretty straightforward algebra problem, 395 Kelvin. Now let's look at the next example problem, something that I think everybody wishes would happen, that they would find a corked bottle with a message inside somewhere along the beach. Periodically you read about one in the news that's been in the water for 20 or 50 or even 100 years, and it's made its way across the ocean sometimes. So again, if I solve both of my equations, PV111 for PV over NT, and then that can also equal PV over NT for the second condition, the second set of conditions. That's how I do it. Your book does it this way, with PV over NT final in the numerator, PV over nRT in the denominator. I think I said PV equals nRT in the numerator of both, PV equals nRT in final initial in the denominator, whichever way works for you. And the n is going to cancel out, and our r is going to cancel out. And so we have this equation right here. Solve the equation for final pressure. And now we find that that pressure, when we plug in our numbers, is this value. That is the pressure that is going to be inside the bottle. Now, if we draw a vector diagram, which I did right over here, you can see that if I want to find the frictional force that will eject the cork because of all the extra pressure inside the bottle, if the cork is going to be going up, then the force of friction will get in the way and it'll be going down. So you can see why I drew my force of friction vector acting down. We also have the air pressure pushing down, and inside we have the force of the gas pushing up. So the up forces are going to equal the down forces, which is what we have down here. And if you remember that force equals pressure times area, that gives us this equation. When the summation of the forces equals 0, and I plug in PA for each force, but I leave the force of friction as is, and subtract the ones on the right side, put them on the left so that everything equals 0, which is the configuration the textbook likes to use. I just usually like to solve it up equals down. Doesn't make any difference. When I plug my numbers in, down here, we get the force of friction at 505.29 newtons. Let's just look at one more problem. We have a sturdy balloon with a volume of 0.5 meter cubed, and notice the mass is in kilograms for the iron weight that's dangling from the bottom of the sturdy balloon. Notice we're making some assumptions. We have a light material, so its mass is going to be negligible, though we do have to worry about the mass of the air inside the balloon. And it is elastic, because when it gets deeper in the water, it's going to be, the pressure is going to make it smaller, and that's going to decrease the buoyant force, which is what it says right here. because the smaller the volume of a submerged object, the less water it will displace, and the buoyant force is the weight of the displaced water. So here's my picture of a balloon right there. And again, I drew my force vectors, and I use different terminology from the book. So here's my force of weight of the balloon, and here's my force of weight of the iron, where Fe is the chemical symbol for iron, pulling down due to gravity. Acting up, I have the buoyant force of the water that is displaced by the balloon, and I have the buoyant force of the iron of the water that is being displaced by the iron block. So the one thing I'm going to have to do is obviously find the volume of the iron, and I can find the volume of the iron by taking its mass divided by the density. Where are you going to find the density of iron? You'd have to look it up on a chart or Google it, or it would be given to you on a test. And I'm also going to have to find the mass of the balloon. Well, the mass of the balloon, right here, is going to be the density times the volume of the balloon. And here you're going to have to find the density of air. That also can be found on a chart or will be given to you on a test. So now I have the volume of my iron, which will help me to find the buoyant force of the submerged iron, because the buoyant force is going to equal the weight of the displaced water, and the displaced water will have the same volume as the iron. And I also now know the mass of the air inside the balloon. So now when I have in this line right here, my upward forces, the buoyant forces, equal the downward forces due to weight. And I use the symbols of the book now in this line right here. I'm using the book symbols, not mine. So what is the buoyant force of the iron? It's going to be this right there. It's going to be the density of the water times the volume of the iron times gravity. And if you think about it, density is the density of the water is going to be the mass per volume of the water, and the water that's displaced equals the volume of the iron. And so technically this ends up being m, the mass of the displaced water, times gravity. And then here's my weight of the piece of iron acting in the opposite direction. So we have the buoyant force acting up right here, and we have the weight acting down right there. We do the same thing for the balloon, the buoyant force of the balloon acting up, and the weight of the balloon acting down. And now I'm going to simplify the equation because conveniently gravity cancels out all the way through. Don't have to worry about the acceleration due to gravity, which means you could do this at any place on the Earth or any planet for that matter that's got water, or if any liquid for that matter. You just have to have a different density for that liquid. And now when I plug in my numbers, I can find the volume of the balloon. So now when I come down here to part B, what is the balloon's pressure at this equilibrium? Once again, I can do PV over NT equals PV over NT, or the book's method, PV equals nRT final, PV equals nRT initial, and the top and the bottom have to equal each other. Again, the R's are going to cancel, the amount of gas is going to cancel, and when I plug in my volume of the balloon down here, and this volume was given to you earlier in the problem, here is the air pressure. You remember that from chapter 9. And now I have my the pressure. This is the balloon's pressure at the equilibrium point, where the buoyant forces acting up equal the weight forces acting down. And now I can go to part C, to what minimum depth must the balloon be to reach this equilibrium? What's the minimum depth? And I remind you of something from chapter 9 over here. If pressure equals force divided by area, and force is mass times gravity over area. And now if I multiply the top and the bottom by the depth, or the height, if you will, beneath the surface, I now have area times height down here, which is also volume. You notice that mgh looks suspiciously like potential energy. And you'll notice that my mass per volume right here is my density. And that's where that equation, that pressure equals density, gravity times height comes from. And so now I just plug in my numbers, and I need to have this depth for the balloon to be at equilibrium. And then the last thing to mention, again, is in chemistry, you might remember that the number of moles equals the mass divided by the molar mass, or I should say grams per mole is the molar mass. I should have that as an M. The molar mass is the grams per mole, the mass of a mole. You might remember that. We're not using that definition here. Over here, we're saying that how many moles I have depends upon the number of particles divided by Avogadro's number. Avogadro's number would be 1 mole. And so what fraction of 1 mole or what multiple of 1 mole would be dependent on how big the number of particles I have. Now, if I take N over NA and substitute it in for N, and so I'm just bringing it down there, I get the equation that you see written. And then the next thing we recognize when I recognize, that Avogadro's number and R are both constants, I can combine those constants and call it K sub B in honor of Boltzmann. We'll run into him in chapter 11, if I remember correctly. Boltzmann's constant. And this is a configuration for the ideal gas law that a physicist might use. You wouldn't recognize it from chemistry because we didn't use it. And incidentally, look at the units for Boltzmann's constant are joules per Kelvin, and that happens to be the units of entropy, which is a measurement of disorder. And we will see that in a later chapter as well.